Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is just do some kind of interesting, challenge type problems. And I want to start off with one of my absolute favorite problems in linear algebra. And we are going to prove that the set of all positive real numbers, where addition is defined really as the multiplication that you know, and scalar multiplication, this symbol, is defined as exponentiation. So like c times x is x to the c, right? This is actually a vector space. And we can just kind of go through and talk about these. And there's some weird things that happen when you get into what the zero vector is and things like that. So the positive, it's important that you realize it's positive real numbers. You basically just have, you can't have negative a half, but you have positive a half and stuff. That's going to actually matter. So let's kind of go through this. So what I'm going to do is I'm just going to say, let's let x, y, and z be positive real numbers, right? And so basically just x, y, and z are in my vector space V, right? And c and d are real numbers. Real numbers, like any real numbers, okay? So it's basically a vector space that's over the field of reals, and the set is built out of positive reals. That's important, okay? So this is just a good example of basically go and show how weird vector spaces can be. Because if you get into it, right, so if you do x, and then this is what we're calling plus here, really would be like x times y, the way you think of it. That's certainly greater than 0. So x, y, well, no, I should probably do it this way. So x plus y is in V, right? It's positive real. For the second one here, basically since x plus y looks like this, which is that multiplication that we're used to is commutative. You can flip that, right, which then by definition is y plus x. And so, it fits our commutivity that we need for the addition operation. Maybe just speed things up here, since multiplication, I'm just going to put that in quotes, the way we think of it normally is associative, our plus operation will be as well. So number 4 here is where things to me get kind of fun. So basically the zero vector, okay, so think of this as bold, 0, basically equals 1, right, like the number 1. Since if you do that, like any vector, I guess, x, and you add it, right, to this 0 vector, it just equals x times 1, the way we're think of multiplication. And then, this is, of course, just x, right? And so, that thing, So 1 is an element of my vector space V because it's a positive real number. So, you can show your parents that I'm teaching you that 0 equals 1 because in this vector space, 0 does equal 1. In terms of 5, basically we need to have a thing where we can add it to something and get the 0 vector, but the 0 vector is 1, right? And so in this situation, negative a vector is 1 over that thing, since here, 1 over x times or plus, right, x, right, is equal to 1, our 0 vector, right? So all sorts of weird things are happening here. And let's see, so now we're getting into scalars. So for scalars, remember this is exponentiation, and if you do c, times u, that is just defined as x to the c, which is greater than 0. So, c, times u is in v, right? And let's see, I feel like I'm running out of colors. We'll go back to green here. For 7, you can do c times, let's try to keep my correct operations here, times x plus y would be equal to, what would that be equal to? It'd be x times y raised to the c, right? And by properties like of exponents, right, that's just x to the c, y to the c, which is the same thing as xc plus yc, which is equal to c times x plus c times y, which is what we wanted to show, right? So this is just a neat byproduct of properties of exponents, basically, to get that. For number 8, figured for time reasons I would just write this all down. So, c plus d times, I should put in, I think I need, that's okay. Times c plus d times vector x, right, is going to be x to the c plus d. And this plus, actually, I was thinking I need to change it, but it actually, the addition of scalars is still the same old addition of scalars. It's only the addition of vectors that is different here. So then we have x to the c, x to the d, right, which is x to the c plus, my plus, multiplication is addition here, x to the d, and then that's c times x plus c times y, which is exactly what I wanted to show, right? And then 9 feels very similar. I'm running out of room, so I'm going to do it up here. So this is 9 up here. Basically, the reason this one works, the reason you can commute these scalars, it's like associativity with the scalars, is that the multiplication is commutative, and you can associate which one you're raising to a power there, right? So I kind of like flip the order around and then group x to the c and then raise to the d. But so that would kind of show 9. And then 10, 10 is really quick, right? Because if I do, this 1 is actually like the number 1, right? So 1 times a vector x, right, is just going to be x to the 1, and certainly that equals x, right? So that still all works out too. But this is just kind of a neat problem. I feel like when I saw this, it really opened my eyes about what's going on with abstract vector spaces. I think it's really, really good to see that, the reason they italicize these additions and scalar multiplications is because they can be super abstract. There are problems out there where the addition and multiplication are not even remotely like operations that you're used to. They can be understood as like rotations of a graph or something like that. Or you can just completely confuse someone and say addition is what you think of as multiplication, and multiplication is exponentiation. And we just showed by going through all this that really that thing is a vector space. So pretty cool problem, and P.S. You're welcome. This problem is awesome. I stand by my claim down there. Okay. So I want to do another one of these problems because I think they can be kind of confusing. So what I want to just do is find a basis for the span of the span of sine squared x, cosine squared x, and cosine 2x in F, which is the set of all real valued functions, basically. So one thing to notice, like right off the bat, we know that, well, hopefully we know, cosine 2x is equal to cosine squared of x minus sine squared of x. So right off the bat, you can see that these vectors, there's some dependence going on, right? This vector can be defined in terms of a linear combo of these, so we can't have all three in here be a basis. So I'm going to make the claim that the basis is actually just sine squared x and cosine squared x. Basically, I'm going to take that out, and then these, still have to span that because this was defined in terms of these, and so if these can basically be shown to be linearly independent, then I've got it, right? And the reason I think these are confusing is, so what we're basically doing, right, is we want A times like sine squared x plus B cosine squared x to equal 0, and we want to argue A has to equal B equals 0. And this is the really important part. I'm going to do it in yellow. It has to be for all x, okay? And I think that's what's kind of confusing, because to certainly, and intuitively, if you think scalar multiples here, the idea of take a set of vectors 1, 2, and then 2, 4, right? This set is not linearly independent, right? Because this is just a scalar of this. And like intuitively think that graphs, sine squared x is not going to be a scalar of cosine squared x, and cosine squared x is not going to be a scalar of that, right? So, you could argue that maybe conceptually to get the idea, but there's like a formal math way to basically do it too. And that's just, we've done this before, but it is a little tricky, and I want to kind of make sure it's clear. So the idea is to basically just set up a system of equations and show that A and B have to be 0, right? So you can do it with anything. You could do, because it has to hold for all x, that's again the important part. So you could let x equal a specific one, like, pi over 4. And then from this equation, right, you would get A over 2, I guess, right? Because it'd be root 2 over 2, which is, you square it, it's going to be 2 over 4. So you get A over 2 plus B over 2 has to be 0. And then we could say let x equal, what's another one that's nice, pi over 3. And then from that, we would get A times, I'm not going to try to do mental math here, plus B times square root of 1 over 2, which I know is 1. So I would get 3A over 4 plus 1 over 4B equals 0. And so then I could just go ahead and make a matrix, 1 half, 1 half, 0, 3/4, 1/4, 0. And the idea here is I'm just I have two unknowns, right? I'm making a system of equations for my two unknowns. And then I can just go and, RREF this. And what you're going to see is basically 1, 0, 0, 0, 1, 0. And so what that implies is A equals 0 and B equals 0. There's other quick ways to do it. If you let x equals 0, right, you would see that, okay, well then B has to be 0, right? But then if you let x equals pi over 2, you're going to get an equation that says A equals 0. And so there's a way to do it quickly with the zeros, but sometimes I feel like it doesn't teach the concept as well, so I like doing it with like other ones. You just need to have two, you're trying to solve for A and B, two unknowns, you need two equations, and then I can just do like a system of equations solving thing, and I get A equals 0 and B equals 0. So long story short, you know, this right here, basically combined with that, says that my set is linearly independent. That sounds good. And then I have a basis, right? That's it. So that's kind of how we can go ahead and try to answer that question, basically. So this is just one of these concepts that I feel like ends up becoming so important in math, and I just feel like I want to tell you about them, even though I know you won't get tested on this kind of stuff. It is something that's definitely beyond our course, but it's really cool, and I kind of want to make sure you just see something about it. So there's a lot on this page, okay? And I wanted to start up here. So there is actually, when we talk about linear algebra and subspaces and abstract vector spaces, there is a formal concept called a sum, okay? And then there's something called a direct sum, right? So if you have, you know, U1 through UM subsets of some vector space V, the sum of these things, denoted by literally just plus, is the set of all possible sums of elements in U1 through UM. So basically, you're getting adding together things U1, 2, 3, 4, 5, where U1 comes from capital U1, U2, capital U2. Basically just adding together a bunch of stuff, right? If you make the distinction be a direct sum, okay, this concept always confused me at first, but I'm going to try to explain it really clearly here. So U1 and UM are still subspaces, and it's direct, okay, which is different than just a normal one, if and only if each element of that sum, so the sum they're talking about up here, can be written in one and only one way, okay, in here. And when that happens, we write U1 with this symbol, circle around the plus, instead of just a normal plus. So I can make a pretty clear example, I think. So if you let U1 equal like the set of things like x, y, and 0, and then you let U2 equal the set 0, 0, z, right? We could say U1 direct sum U2 is going to equal R3, because there is one and only one way to get, like, say, 1, 1, 2 out of adding these two subspaces together, okay? But if instead I do, let's go down here, U2 star now is like the set of things that have the structure, let's say 0, WZ, okay? Now I cannot say R3 does not equal U1 plus U2 star, direct sum U2 star. I can say R3 equals U1 plus U2 star, okay? But it's not unique because I can get, 1, 1, 1 can equal 1, 1, 0 plus 0. This is such hard mental math for me. It can equal that, or 1, 1, 1 can equal 1, 0, 0 plus 0, 1, 1. There we go. So that is not a unique way to get 1, 1, 1, which lives in R3, right? But we could still say it can sum to it, okay? It would be this kind of sum, just not a direct one, right? This direct sum thing plays like a really important role in a ton of higher math. And there's another symbol that is kind of connected to it in math, and that's something called the tensor product. And this is way beyond the scope of our course, but I feel like it's so connected that I wanted to at least show it to you, but I will never test you on this thing because it's quite hard. And the tensor product is like a cross, like a multiplication with a circle. But you might ask, well, what is a tensor? And that's a very good question. Tensors kind of came around, I think they were like early 1900s. And basically a tensor is an abstraction of a vector. That's kind of an easy way to put it. And there's a lot I could say about tensors. This down here, this is actually something called the universal coefficient theorem. And the universal coefficient theorem is something that I worked with a ton in grad school. So you can go to Wikipedia pages on that and read all about it. But this is super, super confusing for me to explain it to you. I'm not even going to attempt. But all I wanted you to see is that, hey, there's a tensor product symbol. It's a thing. So tensor product is kind of like a very high dimensional way of thinking of multiplication. And it arises kind of naturally here because we've been doing this where we can take a scalar from our field and multiply it by a vector. And that's just like scalar multiplication, right? But if we want to multiply two vectors, this is something that just doesn't make sense, right? We don't have u, like vector u times vector v. Well, it turns out that you kind of do if you go into the world of tensors. You can do the tensor product of vector u times vector v. And I shouldn't really even say times because it's really an abstraction of that. Just like direct sum and sums over here are an abstraction of addition. There's a connection here that I kind of want you to see. This is like abstract addition. This is abstract multiplication in a sense. And this is a funny little thing that I saw online. The reason this is so good is because tensors really are the next level of abstraction from a vector. You can kind of think of abstraction with this as like you have numbers, okay, like scalars, right, which we use in like pre-algebra and stuff. And then going up a tier, we have vectors, which now at this point you kind of are getting really familiar with. And this can also be, quite broad now, we're seeing. But then the next level up is tensors, okay? And you might ask, is there more? And I'm not going to get into that right now, but tensors are basically the next level of abstraction past vectors. And so if someone was using tensors to prove a vector identity, it is like this raw strength because it technically works because all tensors of a certain order are vectors. And so if you prove vector properties for that order on the tensor, then you've proven a vector property. So it's funny. But I wanted you to just see that this is a thing, basically, that there's some connection between abstract multiplication of vectors and abstract addition of subspaces.